All right, lesson 1.7a, compositions of functions. It says you've created new functions by using algebraic operations in previous courses. Suppose you want to calculate the cost to air condition your Florida home on a particular summer day. The cost of the cool air will depend on the average daily temperature, and the temperature will depend on the day of the year. Do you see how the two relationships are connected? The cost depends on the temperature, and the temperature depends on the day of the year. This process of combining functions so that the output of one function becomes the input of another is known as a composition of functions. The composition of function f with the function g is defined as f composed of g, which is what that little symbol means there, okay, the little open circle, we'll talk more about it in a minute, is equal to f of g of x. The domain of f composed of g is going to be the set of all x in the domain of g such that g of x is in the domain of f. So, back on this notation, notice in between f and g there's a little circle, but it's not a closed circle. It does not mean to multiply, it means a composition. It's open. Closed circle means multiply, open circle means composition. All right, then the domain here, it says is a set of all x in the domain of g such that g of x in the domain of f. So basically I look at this as like to find the domain of a composition. It's a three-part process. You have to look at the domain of the input, which is whatever you're inputting. In this case it'd be our g of x. You're going to look at the domain of the output. It's the answer when we do the composition, and then your domain of the composition is what makes both of them true. All right, so if I had like one of them was all real numbers, but the other one says x has to be greater than or equal to 0, then the domain of the composition is the fact that x has to be greater than or equal to 0, or from 0 to infinity. All right, so it's what makes both of them true, but you have to look at the input and you have to look at the output. All right, so reading a notation, it says it is important to understand the notation conventions for composition functions. Let's begin with the open circle symbol, which is known as a composition operation. Be sure to note that symbol does not represent the product of f times g. Okay, f of g of x is not equal to f of x times g of x. When reading the notation from left to right in this statement, it says think f composed of g at x is equal to f of g of x. So in general, f of g of x and g of f of x are going to be different functions. So typically you get two different equations. Very seldom we get the same equation, and if you do, those are inverses, which we'll talk more about later. All right, so then it moves on to the composite functions and the commutative property. So the commutative property just means that you're going to have f of g of x, when you take its composition, it will equal the g of f of x if it is commutative, okay? If they're not equal, then they're not commutative. So example 1 says using the functions below, find f of g of x and g of f of x. Can you determine whether the composition of the functions is commutative? And it tells us f of x is 3x minus 5 and g of x is 4 minus x. So we're going to go find f of g of x first. All right, and so we're going to take f and we're going to plug g of x into it. I don't know why I wrote f there. All right, so the way I look at it is f is going to be my skeleton. So it's my 3x minus 5. And then g of x is what we're going to plug into that f function. So that would be the 4 minus x. We plug it in for x. We can simplify this. Oh, sorry. So we're going to distribute the 3. Bring down your minus 5. Combine your like terms. And so there's our composite of f of g of x. Then we need to go find g of f of x, it says. So g is my skeleton now, so it's 4 minus, and we'll plug in for x, and f is what we're going to plug in, so that's the 3x minus 5. Again, we're going to distribute. And we're going to combine our like terms. And so that is our composition of g of f of x. It says, can you determine whether the composition of the functions is commutative? So since f of g of x is not equal to g of f of x, because they're not the same, the composition is not commutative. So it is not commutative. All right, so example 2 says let f of x equal x squared minus 3x, g of x is 1 over x plus 2, and h of x is square root of x. Find a rule for each of the following. State the domain of each function. All right, so let's go through and let's look at A. Now, A is a little bit longer, okay, so I would write small, but we're looking for f of g of x. So that means f is my skeleton, so x squared minus 3x, and g is what we're going to plug into it. So g is 1 over x plus 2. All right, well, to simplify this, when we are squaring a fraction, remember we square the top over the bottom, the top and bottom both get squared, the numerator and denominator. So I have 1 squared, which is 1, over x plus 2 squared, which I'm just going to leave as x plus 2 squared. And then the second part here, we're multiplying with fractions. Well, remember, you multiply the numerators together and the denominators together. So I'm going to make that 3 into a fraction. I put it over 1. So I get minus on top, 3 times 1 is 3. And then in the numerator, 1 times x plus 2 is x plus 2. Now, in order to subtract or add fractions, remember you got to have a common denominator. So one of my denominators is x plus 2 squared. The other one is just x plus 2. So if I multiply the second one by another x plus 2, they'll be the same. So I'm going to multiply this x plus 2 on bottom times another x plus 2. That'll make it x plus 2 squared, just like the other. But remember, what you do to the bottom, you got to do to the top. So I'll multiply the top by x plus 2 as well. So then I'm going to go ahead and combine my numerator. My numerator is the 1 minus 3 times x plus 2 over the common denominator. So you get 1 minus 3 times x plus 2 over my common denominator is x plus 2 squared. Simplify that numerator. Keep simplifying that numerator. And you could work out the denominator if you really wanted to, but it's not going to make anything cancel, so I'm just going to leave it like it is. All right, so there's my composition. And then we got to go find the domain. So remember, the domain is a two-part process. To find the domain, first thing we're going to do is look at the input. My input was that g of x, which is the 1 over x plus 2. Well, remember, we had certain things we talked about when we did domain in them a while back that had restrictions. And one of them was if it's a fraction. So remember, if it's a fraction, the denominator cannot equal 0. And so we could solve this. And so we know that input has a restriction that x cannot equal negative 2, which means the domain of this composition is going to have that restriction as well. Then we got to look at the output. The output is the answer that we got. So it's our negative 5 minus 3x over x plus 2 squared. Well, again, it's a fraction, so we know that the denominator cannot equal 0. We'll square root both sides. So x plus 2 cannot equal 0, which means x cannot equal negative 2. Now, they both just happen to be the same, and so that means that the only restriction we have is that x cannot equal negative 2. But we need to go ahead and write that in interval notation. So remember, that means that our domain is going to be from negative infinity to negative 2, union negative 2 to infinity. All right, I know we normally do not box our stuff, but I'm going to here just to make sure we can see it. So this was our composition, and this is our domain. All right, moving on to B. B says g of f of x, which means g is going to be our skeleton. So it's 1 over x plus 2. And we're going to plug f into it, which is the x squared minus 3x. All right, well, I don't need that fraction on bottom there. I'm sorry, I don't need the parentheses on bottom. And I can't simplify it anymore. If I tried to factor the denominator, it's not going to cause anything to cancel, so I can stop there. Then we're going to go find our domain. So remember, let's look at our input. Our input is x squared minus 3x. Does it have a restriction? It's not a fraction. And the other restriction we had to watch out for was if it was an even root radical. Well, there's no square root, 4th root, 10th root, 12th root, 100th root going on in there. There is an x squared, but that's not a radical, okay? So therefore, there is no restriction when meant it's all real numbers or negative infinity to infinity. Then we got to look at the output. And so our output was 1 over x squared minus 3x plus 2. We do have a restriction there. It's a fraction, so we know that our denominator cannot equal 0. So on the left side, we're going to go do our x box. It's got to multiply to 2, combine to negative 3, so negative 2, negative 1. So we get x minus 2 times x minus 1 cannot equal 0. Set them each not equal to 0. And so we know that x cannot equal positive 2 and x cannot equal positive 1. All right, so then for our domain of the composition, the input says, I have no restrictions, all numbers work for me, but the output won't let us use the numbers 1 and 2. So because the output says we can't use the numbers 1 and 2, the overall domain means we cannot use the numbers 1 or 2. All right, so to write that interval notation means we can start at negative infinity. We're going to go up to the smallest restriction to the next smallest restriction. And remember, you keep doing that until you get to the biggest restriction. The biggest one was 2. And then you go from that biggest restriction up to positive infinity. All right, so again, I'm going to go ahead and box these just so we can see them. This was my composition, and this is my domain. Then for C, we got f composed of h of x. So it means f is my skeleton. So x squared minus 3x. Plugging in h of x. So square root of x squared is x minus 3 square root of x. Then we're going to look at our domain. So we have our input. Our input, which is that square root of x. There is a restriction because it's an even root. So remember, it's got to be greater than or equal to 0. And so that means that x is greater than or equal to 0. Our output, we had was x minus 3 square root of x. We don't have a fraction in there, but we do have a square root. So that square root is our restriction, and it's the same as the input. So it's just a square root of x. So we know we're going to get x has to be greater than or equal to 0. The restrictions are the same in both of them, so that means the restrictions are the same in the domain. We know x is going to be greater than or equal to 0, and we need to write that in interval notation. So it means we're going to start at 0, we're going to go to infinity, and 0 is going to need a bracket because it's equal to. So just to be consistent, I am going to go ahead and box these just so we can find them. And then D. D says h of f of x. So h is it's my skeleton. It's just a square root of x. And then, so we're plugging in f, which is your x squared minus 3x. Now we can't do anything with that. We can try to factor it, but then we just have x times x minus 3. It's not going to do anything with it, so you could just leave it like that. I'm just going to rewrite it without that parenthesis because we don't need it. All right, then let's look at the domain. So the domain, now this one, my output domain is going to take a little room, so be careful, okay? So the input's not too long, but the output is a little bit longer. All right, so my input was just at x squared minus 3x, and so we know it has no fraction, it has no even root, so its domain is all real numbers. My output is that square root of x squared minus 3x. It's a square root, so we know that it has to be greater than or equal to 0. So I can get rid of the square root by squaring it. And so x squared minus 3x has to be greater than or equal to 0. But this is where we run in trouble. Because it's quadratic, it's not so easy to solve. And we did this back when we did rational functions. Or we talked about rational inequalities and everything. This is where we had to find those critical values. All right, so I'm going to go in here. I'm going to find those critical values. And so remember, you find those numbers by setting the equation equal to 0 and solving. So x squared minus 3x equals 0. So then we can factor, greatest common factor, set them each equal to 0 and solve. So we have critical values at 0 and 3. That's where it's going to equal 0. Something's going to happen there near them, though. So when we did this before, we used the number line. And so we have our infinities. And we put our critical values on it. So 0 and 3. And then we picked numbers in between here in these intervals. So like I picked -1, +1, and 4. And we're going to take and plug them into the equation to see, is it going to give us a positive or negative answer, okay? So we're going to plug it into our equation up here. All right, so I'm going to plug in the -1. So I get the square root of -1 squared minus 3 times -1, which is the square root of 1 plus 3, which is the square root of 4, which is 2. That is positive. I'm going to plug in 1. So 1 squared minus 3 times 1. So it's 1 minus 3, square root of -2, which is I square root of 2. It's neither positive nor negative because it's imaginary. So what that means is if I looked at the graph of this, there's nothing going on in between the 0 and 3. It's blank because it's not on my imaginary numbers, not on my x-axis. Okay, or my x or my y. All right, and then I'm going to plug in 4. So I have 4 squared minus 3 times 4, which is 16 minus 12, which is square root of 4, which is 2. So again, this is going to give me a positive answer. Now when I look over here, I'm looking for where it's going to be greater than or equal to 0. Remember, greater than 0 means I'm looking for positives. And so I can see my two intervals. So my two intervals are going to be over here and over here. So from -infinity to 3 with a bracket, because it's greater than or equal to, union, I'm sorry, that should be a 0. My bad, hold on. -infinity to 0 with a bracket, union, and then 3 with a bracket to positive infinity. So again, here's my domain. Well, hold on. I made another little mistake. All right, so that's the domain of my output. Let me rewrite that down here. So -infinity to 0, 3 to infinity. But my output says we got this restriction. My input says we have no restriction. So we only have that one restriction. So our domain of the composition is the same as the domain of the output. I apologize. All right, and then there was our actual composition. All right, example 3 says use a graph of f and g to evaluate the functions. So remember, most of the time we see it written as like f of x equals something or g of x equals something, like right here, okay? So when we're looking at A, f says f composed of g of 3, so I'm going to rewrite that as f of g of 3. When you're working compositions, you work from the inside out. So on the inside here, I have g of 3. So we're going to go to our g graph, and remember, it's usually g of x, so that means that that 3 there is our x value. So we're going to go to our g graph, and we're going to go look where x is 3. So I'm going to go up and find my graph, and what is its y value? 1. So we know that g of 3 is equal to 1. So then I'm really just looking for f of 1. So I'm going to go to my f graph, go to where x is 1, and what is its y value? 2. So we found f composed of g of 3 is equal to 2. All right. B wants f of g of 1. So again, we're going to start with the inside. So we're going to go find g of 1. So go to your g function. When x is 1, the y value is 3. So no, that's 3. So I'm looking for f of 3. So I'm going to go to my f function, go to where x is 3, the y value is 2. So this is all going to equal 2. C says we're looking for f of g of 4, and we're going to multiply that times g of f of 1. So I'm going to go find f of g of 4, then I'm going to go find g of f of 1, and then we're going to multiply those numbers together. All right, so remember, start from the inside out. So g of 4, so I'm going to go to g function. When x is 4, it's right there, its y value is 0. So now we're looking for f of 0. So go to your f function. When x is 0, its y value is 4. All right, times. And I'm going to go work the other side here. Looking for f of 1. So f of 1, so I'm going to go to my f function. When x is 1, go up, its y value is 2. So then I'm looking for g of 2. So I'm going to go to my g function. When x is 2, its y value is 2. And then 4 times 2 is 8. So these two things multiplied equal 8. D, we're just dividing. We're going to do the same thing. We're going to work the numerator, we're going to work the denominator, and then we'll actually divide it out. All right, so my numerator says f of negative 1. So I'm going to go to my f function. I'm going to go find when x is negative 1. Let me erase what's on there. All right, sorry. So go to your f function. When x is negative 1, what is its y value? 6 over. And on bottom, we get f of g of 3. So start with the inside. Let's go find g of 3. So go to your g function. When x is 3, its y value is 1. And so we're looking for f of 1. So now I'm going to go to my f function. When x is 1, its y value is 2. So I'm going to put a 2 there for the denominator. And then I'm just going to divide. 6 divided by 2 is 3. All right. Then E and F are like we did on A and B. So E says we're going to take F composed of G of 4. So F composed of G of 4. I'm going to work from the inside. So I'm going to go find G of 4. So go to my G function. When X is 4, we know its Y value is 0. And so I'm looking for f of 0. So go to your f function. When x is 0, its y value is up here at 4. And then we have g of f of 2. Work the inside. So f of 2. So go to your f function. Go to where x is 2. Y value is 0. So we're looking for g of 0. So go to your g function. When x is 0, I hit something. When x is 0, its y value is up here at 4. All right, then we're going to do the opposite. So now we're decomposing functions. So when you decompose a composite function, you're finding the components of the composition. You're looking for an inner function and an outer function. So example 4 says for each function h, find the functions f and g such that h of x is equal to f of g of x. So g is our inner function because it's on the inside, and f is on the outside, so it's our outer function, okay? So when we talk about on the inside, we're literally looking for something that's inside parentheses, inside absolute value bars, inside a radical, inside a denominator, inside a numerator, inside the exponent. It's inside of something. It's got x in it, but it's inside of something, okay? That will be what our g of x will represent. And then what we'll do is once we find it, we replace it with an x, and that's going to give us our f of x, our outside function. So look at A. H of x equals x plus 3 squared. We can see that x plus 3 is inside the parentheses, so it's going to be our inside. And so I'm going to come over here, and then I'm going to just replace it with an x. What we see written there now is literally our outside function, which is just that x, and we still had the square there. And you can double check it. So you can do the composition of f of g of x. So if I take f of g of x, f is my skeleton, so x squared, and g is what I would plug in. Is that what we started with? It is, so that means we did it right. All right, so let's try b. H of x equals 1 over x minus 5. Notice the x minus 5 is inside the denominator. So I'm going to write it for my inside. It's my g of x. I'm going to put a little x over it. And what we see written there now is our outside, our f of x, which is just 1 over x. On C, notice we have an x plus 2 inside that radical. So I'm going to replace that with an x. And so my outside, now what I can actually see there is just the square root of x. And then D is trying to trick us. It has x minus 2 squared minus 4 times x minus 2 plus 5. But notice, both inside the parentheses is an x minus 2. So x minus 2 is going to be our inside, and because it's there twice, we're going to put an x on both of them, which leaves us x squared minus 4x plus 5. Now, all of these that we just looked at only had one way to write them. But sometimes compositions can have, you can decompose them in more than one way, all right? And so example 5 tells us let h of x equal the square root of 3x squared plus 1. Write h as a composition of functions in 2 different ways. I can see 3 on there. One of them, just like what we just did, and the other 2, we can find different things, but be careful because inside here you have multiple things going on. You have multiplication and you have addition. You can't mess with PEMDAS, okay? You can't do like an x squared plus 1 together because the x squared needs to be multiplied times a 3 first. So we'll talk more about that when we get to it. So let's go ahead and let's do our first one like we did up above. So what's on the, so first thing, oh wait, before we actually do that, I'm going to put here that we're going to let h of x equal f of g of x. So that way we can identify g of x is our inside. So most of the time when they do this, they'll write f of x first, and then they'll write g of x. Just because f of x is written first doesn't mean you have to find it first. Find the inside first. Find your g of x. So on h of x here, what's on the inside? The 3x squared plus 1. So I'm going to replace that with an x. And so I can see that f of x is just the square root of x. But it said 2 different ways. So let's see another way. F of x and g of x. What else could be on the inside? Well, it's probably going to be inside. But notice we have that 3x squared together there, don't we? So let's let 3x squared be our g of x. So then if I take and put an x over it, my f of x is the square root of the x plus 1. All right, and I know it said to only find 2, but for grins and giggles, let's find a third one here. All right, so what else do I have inside? Well, we have an x squared and a plus 1, but if I take and try to just put that as my inside, I just messed up the rule. I just messed up the rules of PEMDAS. I'm going to try to add before I multiply times 3. We can't do that, so that's a no-go. But what if I just let the inside be x squared? If my inside is just x squared, then when I go here and I put an x over the inside, I haven't messed with PEMDAS, I'm still multiplying. So my f of x will be that square root of the 3x plus 1. And if you're unsure if it works, try it. F is going to be your skeleton, so 3x plus 1, and plug in g of x. Did it work? It did. So we know that our decomposition works. All right, so that's 3 that I saw. I don't think there's any more on that one, but some of them will have only one, some could have 2, some can have multiple. All right, interpreting composite functions. So example 6 says Jim plants wheat on his farm in Kansas. The function W of A gives the amount of wheat in bushels that he expects to harvest if he plants wheat on A acres of land. When the wheat is harvested, Jim can calculate the amount of money, M, in dollars that he'll be earning from selling a bushel of wheat with the function M of W. All right, so we have two things there. We have W of A and we've got M of W. So look at A. It says explain the meaning of W of 5 equals 275. Well, when I do W of A, this is going to be the amount of bushels for the acre, okay? When we have M of W, this is the money from the bushels. So when it's W of 5, 5 is my acre and 275 is the bushes. So 5 acres yields 275 bushels. Or you can say we get 275 bushels when we have 5 acres. Something like that, okay? M of 65 equals 550. Well, the 65 is the bushels, so 65 bushels is going to give us, M is your money, so it's going to give us $550. And then explain the meaning of M of W of 4. Well, remember it's W of A, so the 4 is going to be my acres. Whoops, sorry. But M of something equals the money. Okay, so 4 acres of land will yield that money amount, so the 2,100. So 4 acres of land yields or gives us, provides us $2,100. And that is the end of lesson A.